can begin.
Hey, so my name is Jonathan Stancill, and my project is called the Macaw, or a magnetically conning accelerator for watercraft. So the basis of my research was to find a way to reduce noise pollution and carbon emissions in our oceans. And I realized that the source of that kind of comes from the engines that we use to move our watercraft. So I realized the best way to reduce this is actually just stop producing it by changing the engines that we're using. So a lot of people kind of have heard of noise pollution before, or sorry, not noise pollution, just carbon emissions before, but they haven't heard of noise pollution. And noise pollution is when you have a lot of background acoustics in an environment, and those lead to interferences with the other noises that are supposed to be in that environment. So an example would be how whales communicate when they're traveling in pods. If you have a massive cargo ship going by, the engine noise from that will interfere with the communication between the members of the pod. And that's how you end up with individual whales getting separated from their pods, which is part of why they're endangered species because it's really hard to see one whale. And so you're very likely to injure them with either the prop of the ship or kind of hitting them with the hull, which is bad for both the whales, but also for the shipping companies because the cost they have to spend on repairing the ships, and it's also a loss of profit because the goods don't get where they're supposed to go on time. And so what I did is a continuation from last year. So last year's project was this. It's a really rudimentary design that I used as a proof of concept to show that my ideas would work. And so what it was is a electric field running from cathode to anode through the water. And then parallel to that, you'll run a magnetic field. And that's where you can start to utilize a physics principle called the Lorentz force, which is where when a magnetic field and an electric field meet at right angles, any charged particles where those two intersect will experience this Lorentz force and be moved in the third direction out the back of the motor. So once I'd kind of done the math to realize this and see that it was going to actually produce measurable thrust, I built this prototype and I was able to test it and show that it did produce thrust, but it also stayed under 60 decibels no matter what power level it was at. And 60 decibels is kind of where you want to stay because that's going to be quieter than if just outside and the breeze is blowing. So a really quiet unit, and the only increase in noise happens when you increase the power and the water is moving faster. The unit itself doesn't actually make any noise because it has no moving parts. And so moving on to kind of what I did this year, you can see the pictures I have of my new design. It's this right here, which is very different from what I had last year. It's much lighter. So last year's unit was roughly 5.5 kilograms, and I've been able to cut weight completely down to right under 400 grams. So about a 20% weight reduction. And then I was also able to get a lot more power. As you can see in this bottom graph, the purple is power, is the output speed of the water from the new unit, and the blue is from the old unit. And I was able to do this because I found in my experiments that the way to get more speed out of the prototype is to increase the strength of the electric field, but also to increase the time the water is being affected by the magnetic fields and the electric fields. Because the magnetic field isn't going to give you any more power. It just aligns the particles in the right direction. So it controls, like kind of like a transmission. It does forwards and reverse. And then the electric field is kind of like your accelerator in a car. It's what's going to give you more speed so you can go faster or slower. And then the increased length is just kind of a principle of basic physics. When you're being accelerated for longer, then you reach a higher speed. And so I was able to use all that to make this new prototype. And then I also switched the materials I used. So the old one was made out of zinc coated steel pipes and then a 3D printed interior shell. And the 3D printed plastic I used was PLA, which is very brittle. and doesn't hold up very well under chemical weathering or UV radiation. And this year I was able to use ASA, which is much more chemically inert, and it won't react with the salt water, or anything that kind of microorganisms living in the water aren't going to really be able to interact with it. And so since it's much stronger than PLA, I was able to make the outer shell out of the plastic instead of out of the metal, which meant I could keep the metal on the inside. So I was able to use a lot thinner metal of aluminum foil. So that helped me cut weight as well, which is where I was able to get a much higher power to weight ratio, roughly 80 times the power to weight ratio of last year's design. And then the way I measured my output speed is I took a scale and put it in a plastic bag and put that behind the unit when I was testing it in the water. And I was able to measure like the weight of the water that was coming out, if that makes sense, pushing against the scale like this. And so doing that, I could use the force is mass times acceleration. And since I knew roughly the mass that was affecting the scale based off of surface area, I could then take that surface area and convert it to weight of the water and do the force divided by the mass to find my acceleration. And then I could take my acceleration and integrate it over the length from the end of the prototype to the scale to find my foot velocity. And so I'm kind of able to take these findings and see that this would actually be a usable design for going forwards, which was a big problem that a lot of judges had last year with my prototype, was that they couldn't really see how it would be useful because I didn't have a lot of data on power output and whether or not it was like showing promise. But now I have data that shows that the prototype I've designed is actually more powerful, like per pound, than most of the engines we use today for boats, and it's also purely electric. And so what that means is you wouldn't need these massive diesel engines to power the ships. You could replace them with either like a small nuclear power station that a lot of boats have, or you could use a lot of electric batteries, kind of like cars do. You just like an electric car is a bunch of stacked smaller cells. You could just take those larger cells made of smaller cells and stack them, and then you would be able to, based off of this design, it'll fill with water through these channels. And so you can replace the ballast sections of these big ships with that. And since it fills with water, the engine itself acts as the ballast. And since you're no longer using the ballast for just dead weight, you're using it for engine space, and then the old engine space is being used for power, you don't have to sacrifice any cargo space on the ship itself, and you're actually using old wasted space to create power to move the ship forwards. And that's kind of the end of my presentation. I usually ask the judges then if they have any questions.